T point inverse point 2T.
Yeah, that's what I did. And then I did the one minus. Yeah, it's in one minus. Maybe it's the way that I put it. You're supposed to put one minus.
Alright, everybody ready to get started?
Fun?
Today we will, yes,
Fun begin?
today we will talk more about this sampling distribution of sample mean type stuff.
First half.
Although we will just apply it to a slightly different context.
We're changing the word a little bit and we're doing the same thing over again.
Yeah, that's right. That is exactly what we're doing. We're changing the words a little bit, wording a little bit, and we're doing the same thing over again. Specifically, we're gonna do it with, instead of means, we're gonna do it with proportions. And then instead of means, we're gonna do it with mean differences and proportion differences. But it's all pretty much the same thing. We'll take some time going over those concepts and going over some problems. So we will be here most of the class tonight, but I don't think there'll be anything that will confuse you. It'll just be a chance to work these problems, look at them in a slightly different context. Alright, so let's start with some review of class 2 and 3. Specifically this sampling distribution of the sample mean stuff. I'll go over these questions really quickly, remind you of the answers, then we'll go back through them, make sure that everyone's good on this before we move forward. Question 1, what is the sampling distribution of the sample mean? This is a frequency distribution of a very large number of sample means. What is the mean of this distribution? So the center point of this distribution, which we know is a perfectly shaped bell curve, normally distributed. The center point, the mean, median, and mode of that is the true population mean. So you're trying to find that true population mean, so you sample for it. The most likely outcome, or the most common, I said that wrong, it's the most mode means the most common outcome. Doesn't necessarily mean the most likely outcome. So the mode, the median, and the mean are going to be the true population mean, aka the right answer. Sometimes you're going to get a little bit higher than the right answer when you sample, sometimes you're going to get a little bit lower than the right answer, but it's going to fall into a predictable normal distribution. What is the shape of this distribution? As we said, a normal bell curve. Is the standard deviation of this distribution smaller than that of the parent population? Yes, it is. The sampling distribution of the sample mean has a smaller standard deviation. Remember, it is skinnier and taller. The reason for that is the chances of outliers are much less likely. So if you're looking at a whole sample population of, say, Mercy College students who flip a coin 20 times, write down the number of times it comes up heads, the chances of one of those Mercy College students flipping a coin and it coming up heads 16 times, suppose, alright, maybe there's a 1-2% chance of that happening. It could happen 1% of the time. But then if you're going to look at a sample of 30 students, what are the chances that all 30 of those students will average out to 16 heads coin flips? Not happening. So the chances of those kind of outliers, which would throw off your sample mean drastically, very, very tiny. So what that equates to is a smaller standard deviation, and as we say, a taller, skinnier bell curve. If you calculate the sample mean using proper sampling procedures and sample size, what is the probability that your sample mean will be within 2 standard deviations of the true population mean? I'm going to let one of you all answer this. 93, is that your favorite radio station? 93.
97.2.
Not an option. 95 point. It is 95.5. Alright, any normally distributed data at 95.5% of the data will be within 2 standard deviations. And what we know about the sampling distribution of the sample mean is it is normal. That's why we can confidently say that this particular sample mean that we just sampled is going to be within 2 standard deviations of the true population mean 95.5% of the time.
That's. Oh, they asked the question, I can't answer that shit the right way.
Oh, the multiple choice question?
Yeah, I mean, I can't, I was just gonna submit the work, the Excel, but they asking, and you saying not just to say, what you call it, and undefined and defined. Why you can't just say undefined, defined, and leave it, well, leave it as that?
Are you talking about the Excel?
Yes.
Okay, yeah, I don't remember. I don't remember
Oh,
exactly
okay,
which question
so,
about the Excel.
okay, good, don't forget about that.
Okay, alright, let's take it from the top, get you all engaged in this. What is the sampling distribution of the sample mean?
This is the frequency distribution.
Kelsey?
No, let it say, you have the whole sentence, all I know is frequency. The frequency distribution of a very large sample mean,
Very large what?
sample population?
No.
Sample mean?
No.
It's the frequency distribution of the means of the sample. It's the sample, all the sample means.
Yes, very large number of all the sample means. That's an important distinction. So it's a bunch of sample means. Remember we talked about some poor researcher who's gonna take sample means over and over and over again, 30 times at a shot? It's important you understand that distinction because that's what gives it the power. What is the mean of this distribution?
True population.
Monica?
True population?
Yes, the true population what?
That's what
For the standard.
Mean.
True population mean. Yes, fantastic. What is the shape of this distribution and why? Normally distributed?
In a bell curve.
Yeah.
Bell curve? Okay. Anyone want to take a shot at why? Alright, this is always a hard one.
Because it's average out to.
Yeah, average out. You could say law of nature, that whole thing we discussed in class 1. Central limit, yes, central limit theorem. Fantastic. Central limit theorem is a great answer. Is the standard deviation of this distribution smaller than that of the parent population? Why?
Yes, it is.
Yes.
The probability.
Yes, because it's taller and skinnier. Why is it taller and skinnier, Amanda?
Because it's the smaller population, so the deviations are smaller,
Yeah, why are the deviations smaller?
because it's a sample.
Yes. Why does a sample make the standard deviation smaller?
The more we sample, the closer we get to the actual number.
And
Okay, I like where you're going with that. So more of a sample.
and the least likely to have outliers.
Yeah, that's what I'm looking for. Very unlikely to have outliers. I think
Okay.
Adamus's point is interesting. So he's saying the bigger the sample, the closer we're getting to the whole population. I like that on one level. I'm skeptical about that on the other level.
All right.
On one level, like we are getting a bigger sense, a better sense the bigger our sample size is. But the thing is, the whole thing that makes this work, that allows us to take a very small sample size, is because of the fact that the outliers are extremely unlikely. So we can still take what is a fraction of the whole population and get a reasonably accurate measure. Alright, so if you calculate the sample mean using proper sample procedures and with proper sample size, what is the probability your sample mean will be within 2 standard deviations of the true population mean? 95.5. Fantastic. Alright, so let's do that same thing with estimating a population proportion. Proportion is a percentage. Alright, what is the percentage of people who support Bill de Blasio? So it's a number between 0 and 100%. Mathematically, it's handled just a little bit differently than a mean. A mean, like the mean income, it could be any number, from 0 to infinity. Or technically, if you're doing something that could have negative numbers, it could be negative infinity to infinity. So proportions are handled slightly different, in a slightly different manner. Then we're gonna estimate the differences between two population proportions. So this is the proportion of people who support Bill de Blasio in Staten Island. Here's the proportion of people who support Bill de Blasio in Brooklyn. The difference, well, our sample says the difference is 20%, but that's just based on a sample. We'll use a sample mean type of thing to build a confidence interval around that 20%. And then estimating differences between two population means. Town 1 income is 50,000, Town 2 income is 40,000. What's the difference between them? 10. Okay, so we're not gonna be able to ask every single person in Town 1 and Town 2, we're gonna sample here, sample here. Our point estimate is gonna be 10, but we'll need a confidence interval, just like we've used confidence intervals for regular means. Alright, so those are the three topics tonight. Let's start with proportions. When we talk about proportions, we'll just talk about what they are. We'll learn this thing called the sampling distribution of the sample proportion. Just change the words around a little bit. We'll find that that has predictable sampling distribution properties, just like the other one did. And we'll be able to use those predictable properties to build a good confidence interval. So, examples of proportions. 92% of Mercy College students work full-time. It's a percentage between 0% and 100%. 43% of residents support the new tax bill. 60% of voters support Bill de Blasio. That's what we mean when we say proportion. A proportion can either be written as a percentage, like this, or it can be written as a decimal between 0 and 1. How do we write this as a decimal? 0.92, fantastic. Now one thing about percentages that makes them a little bit different when we deal with them from statistics, or from a statistics standpoint, is that there's only two outcomes to a proportion like this. Typically, as long as you structure your questions with two outcomes. You could do three outcomes, but we won't really deal with that right now. For our examples, there'll only be two outcomes. So, if someone calls you and says, will you be supporting Bill de Blasio? All you can say is yes or no. Doesn't matter how much you hate Bill de Blasio, you can still just say no. You can scream no into the phone really loud, but the person doing the sample would just mark that's a no vote. So the end result is going to be a percentage of people who say yes, and it's going to be those two outcomes. We won't have those extreme outliers like we do when we deal with means. So if we're doing a mean income in town, one really rich person can skew our data. Proportions, we don't have standard deviation in the underlying population. So there's no standard deviation to the underlying population in a proportion. It's just the percentage. What is the percentage? And that makes it a little bit easier when we're dealing with sampling. Alright, so some notation. This pie-looking symbol, this is the population proportion, the true population proportion. If we were to ask everyone in New York, do you support Bill de Blasio? If we were to get correct information, this is what it would come out to be. This is what we are trying to find, typically. What is the true population proportion? How do we find it? Well, we take a sample, and we notate it with this little P with the bar over its head, P bar. And we will determine how confident we are that that sample proportion is reflective of the true population proportion. Okay, what do we have here? So take a look at the title of this slide. Think about what that title means, and based on the title, what is on this slide. And I want you to take a look at this pie-looking symbol, which is in the middle of this distribution. And then I want you to take a look at this little symbol and tell me what you think that means. I'm gonna start you off with this symbol right here, this P with the bar over its head, that is sample proportion. And why that's there is that just is telling you that this frequency distribution is a whole bunch of sample proportions. Alright, so that leaves 3 things for you to tell me. 1, read the title, tell me what it means, tell me why this is in the middle, and tell me what you think that is. Alright, so first volunteer to read the title, tell us what that is.
Sampling distribution of the sample proportion.
Yes, what is that, Carol?
It's just a sample of the distribution
What is the sampling distribution of the sample proportion?
of the population proportion, no?
What would that be?
It's just a sample.
The population, the true population
It's a sample.
of the sample proportion.
Is it a sample of the sample?
Alright, so I like to answer this question the same way I answered the one when we dealt with means. It starts off, it's a frequency distribution
Okay.
of what?
Of a sample.
Proportions of all the
Of
samples.
a sample.
Of a sample proportion?
Oh, just sample proportion.
All of the sample proportions. Yes, yes. A frequency distribution of all of the sample proportions. Sometimes I just say a large number of sample proportions, but technically, to be technically correct, it is all the sample proportions. So, we've got some poor researcher calling people in New York saying, do you support Bill de Blasio? A sample of 100 people or whatever, and finding the percentage that say yes. The researcher writes that down, then the researcher goes and asks another 100 people, writes that down, puts them all on a frequency distribution, does that over and over and over again, makes a little notation, and then graphs it. These are the results of 50,000, 100,000, I don't know, 1,000,000 sample proportions. What is this thing? Where is it? What does it mean?
Population.
The true population.
The true population mean, also known as the right answer, right? The percentage of people that really do support Bill de Blasio. Why is it at the center of this frequency distribution?
It's a yes or no question.
Okay, okay. That's not 100% relevant right now, but good thought. Why is this at the center of this frequency distribution?
Because it's a normal distribution.
Okay, normal distribution, why is this at the center? What's the mean
Because
of
that's
this?
the mean of the sample proportion, the overall mean.
Yes, it is the mean of the sample proportions, we know that by looking at the graph. We can look at this graph and say, what's the mean of this sampling distribution sample proportion? It is that, but why is it that?
Is that the midway point between both answers?
Because there's only 2 possible answers, there's a 50-50 chance. So it's in the middle?
It's the frequency that showed up the most.
It is the frequency that shows up the most. Why would this one show up the most?
Is it the right answer?
Most accurate.
Yes, yes.
The most accurate?
It is the actual answer. It is the true answer, the right answer. So it is going to be our most common outcome.
So it's the mean, median, and mode is what you're saying.
Yes, it is.
That's a lot of mix up, it makes you confused. Cause you just
So-
think the truth.
So Roxanne, we're trying to determine the true population mean.
So it's the most common, that I understand, but why is it at the center? It's just because it's the largest frequency, that's the answer that we receive the most, that's. the
Okay,
answer,
it
right?
is, well, okay, so multiple reasons. One is the answer we receive the most, but also sometimes we're gonna be a little bit higher than the right answer, because we're just gonna happen to talk to people who like Bill de Blasio a little bit more. Sometimes it's gonna be a little bit lower than the right answer, we're just gonna happen to talk to people who don't like him. Sometimes it's gonna be a lot higher, but there's an equal probability of a lot higher and a lot lower. So sort of that group of people that like him a lot more is going to average out to the group of people who like him a lot less that we just happen to have in that particular sample. That's another reason why the mean is going to be the right answer. Because not only is it our most common answer, but it is, as long as there's no bias in the way we're asking questions, then equal probability being a little bit high, and equal probability being a little bit low. Okay, so sampling distribution and sample proportion is a frequency distribution of a very large number of sample proportions. It has that same quality of the right answer being the mean of the distribution. It also has that quality of being normally distributed. So we can predict any one sample is going to have a 95.5% chance of being within 2 standard deviations of that mean. Speaking of standard deviations, what do you think this symbol means? Can someone just read this part to me? I'll take the thing on the other side of the equal side. Just read that to me.
Standard deviation of the sampling distribution of the sample proportion.
Fantastic. Alright, so you see that little funny looking O, you know standard deviation of what? Well, it's the little key with the bar over its head. That means sample proportion. So it's a standard deviation of the sampling distribution of the sample proportion. Now we also get to call that standard error. Yes, Kelsey? Alright. So, now, there is no standard deviation in the underlying population. So this standard error is just based on math of how close the proportion is to 50%. And I'll discuss this for a moment, but don't get confused by this discussion. You with me? I'm going to tell you kind of why this is the way it is, but when you need the standard error, you're just ultimately going to use this equation and crunch it out. Make sense? Okay, so let's look at this top part here. This population proportion times 1 minus the population proportion, that is going to be bigger when the proportion is closest to 50%. The reason for that is if the proportion is 50%, you have more diversity in the opinions. So you have half the people over here, half the people over here. So when you sample, you're going to have more dispersion in your sample proportions because you're going to be more likely to get more different opinions. You okay with that? If, on the other hand, it is further away from 50%, if it is, say, 90%, then we are less likely to see dispersion in our sampling distribution of the sample proportion because most of the people we ask are going to have the same opinion. If we want to talk about that some more, we can, but I think we'll just leave it at that for now, and you'll just use the formula. Okay. So, this sampling distribution of the sample proportion, it is a sampling distribution, probability distribution of all possible values of the sample proportion. Let's learn a little bit more about this. Based on the central limit theorem, as Tay reminded us, with large enough sample sizes, this frequency distribution is normal. And if it is normal, then we can predict how confident we are that our sample proportion is accurate. Now, big enough is a little bit different. When we said sample size being big enough for means, remember what sample size we like? 30 or more for sample means. For proportions, just a slightly different calculation. There are 2 formulas, and we need to make sure both of them are satisfied. This one and this one. I'm going to talk about those 2 for about 5 minutes here, but just as I mentioned with the standard error calculation, don't get confused by anything we talk about with these. We'll just get a little background, a little rationale, we'll think about it for a few minutes, but don't let it confuse you. because technically I can't quiz you on this because you won't, it's just the way it works. You won't be able to answer this until you know the end of the answer and it's the beginning, so it's nothing I'm able to quiz you on, it's just something I'll give you a quick little background on. So, the way these equations work is that the closer the proportion is to 50%, the smaller sample size you'll need. The reason is because if the proportion is close to 50%, it won't take you very long to realize the diversity of opinions. You'll only have to talk to 2 people before you're likely to hear both opinions reflected. So you'll need a smaller sample size if the proportion is closer to 50%. If, on the other hand, the proportion is far away from 50%, say it's 1% or 99%, those are both going to be the same thing, so let's just say it's 1%. You're going to have to talk to 100 people before you would even expect one person to say yes. You with me? So say Bill de Blasio's approval rating is 1%. How many people do you need to talk to before you find one person who says, yes, I approve of the job Bill de Blasio is doing? 100. You need to talk to 100 people before you even realize the 1% that are supporting him.
The one, right?
The one. The 1%. You're the 1%. I found it. Okay. So, alright, so you're going to need a bigger sample size if the proportion is further away from 50%. Excuse me. Okay, and if we were to work those out, we would see that sample size or proportion of 50%. Actually, let's just do it. Let's do. I've been talking theoretically at you for a while, so let's just do one of those. So let's take this first one. So it is n times the true population proportion times 0.5, say it's 50%, must be greater than or equal to 5. So what we do is we solve for n in this case. So we divide both sides by 0.5. So let's divide by 0.5 here, divide by 0.5 here. Alright, this 0.50. So this cancels, and the equation remains n greater than or equal to, what's 5 divided by 0.5? 10. Okay, so if the population proportion is 50%, our sample size must be greater than or equal to 10. Suppose, on the other hand, the population proportion is 1%. Alright, so we have n times 1% must be greater than or equal to 5. So let's solve for n. Divide both sides by 0.01. Divide by 0.01. So this cancels. So we have n must be greater than or equal to, what's 5 divided by 0.01? 500. So if the proportion is 1%, our sample size must be greater than or equal to 500. Okay. Alright, so just some context there. Like I mentioned, that's not something that I can really quiz you on, but it's something I want you to have just in the back of your head and in your statistics tool belt. Pull it out of the tool belt. Alright, so this is our standard error, also known as standard deviation of this sampling distribution of the sample proportion. It is this equation, and we talked about a little bit about the logic of that equation. In this case, closer to 50% is going to give us more diversity of opinion and a bigger standard error. Alright, this should look fairly familiar to you. We've got this P with a little bar over its head, which we now know is the sample proportion, the proportion that we collected, plus or minus, this is Z times this square root looking thing. And remember the square root looking thing? We just found out this is the standard error, also known as standard deviation of the sampling distribution of the sample proportion.
So with the previous formula, we usually don't get the population proportion all the time, so can we assume that the sample proportion is what that is?
Great question, great question. So in this is our, and I'll answer that. This is our confidence interval. So we're gonna take our sample proportion plus or minus some number of standard errors. And we realized how to calculate standard error with this formula. And the sum number of standard errors is going to be based on that Z value, just like we did with sample means. If we want to be 95.5% confident, what's this Z value going to be?
1.96.
It's technically going to be 2. I threw you a curveball. I said 95.5. 2 is the right answer.
It
If
is
we want to,
correct.
yeah, it is 2. And if we want to be 68.3% confident, this is going to be 1, or whatever our desired level of confidence is. Now, what Tay pointed out is this is the true population proportion, and when we're sampling, we don't know what that is. That's the whole thing we're trying to find out. So what do we do instead? We substitute the sample proportion that we find in our data for the true population proportion. Can you see that on your slides? It's just the same thing with the P with the bar overhead substituted in. Yes. Since we do not know the true population proportion, we substitute in our sample proportion that we find in our sample. Should we try an exercise? Fantastic. Go ahead and turn to page 282. Let's take a look at number 12. We'll do what we always do, just look through that, try to think about where you think the numbers go, explain them to your neighbor, and then we'll come back together and make sure everyone understands this. Alright, right.
Yeah.
How you feeling with this?
Good.
Excellent. Yeah, need your fuel.
For 97.50, right?
Do we need a couple more minutes, or should we do this? Do it? All right, fantastic. So in this case, we're just given the numbers. We're given a sample proportion of 65% out of 100 points of data. But that is just a sample. We need a confidence interval. So our confidence interval is going to be 65% plus or minus some amount. That some amount is going to consist of the number of standard errors based on a z-score, and it's going to consist of the standard error. Let's do the number of standard errors first. What is the z value for 90% confidence? 1.65. Everyone good there? Do we need to explain that? I'll do it. Okay, 1.65. And what is our standard error? Now we have the calculation, the formula for it. The sample proportion times 1 minus the sample proportion, divided by the sample size, square root that whole mess, what does it come out to?
0.047696996.
0.0476.
9696.
Okay, good. Alright, so 1.65 times 0.04769. And you keep this whole number in your calculator, of course, store it, don't round it, or keep it on Excel, multiply it by 1.65. What do we get if we just multiply those two together? What is our margin of error?
You gotta move.
0.07869.
Alright, so, and don't round this either, keep this in your calculator before you subtract it and add it from 65. But just for illustration purposes, we're gonna take 65% plus or minus 7.8%. That's gonna be our confidence interval. So we're gonna take 65% minus that, what do we get on the lower bound?
I got
Wait,
0.5713.
How much?
Take away.
0.5713.
0.5713, like Roxanne?
Yeah.
Okay, I like
Yeah,
that.
she got a 0.513, that's.
What do we get for the upper bound?
Oh.
0.7286.
Okay. I'm liking those. How about you all?
7.
So this is 65% plus about 8% gives us 72. 65% minus 8% gives us about 57.
Right. So
Okay.
what you say is in between the population standard,
Yeah,
deviation population is in between.
the true
True.
population proportion is between these two numbers.
Yeah,
And how confident are we about that?
be 90,
90%. Okay,
and that's what I gotta write on that Excel thing you have on there.
fantastic. So the interpretation is, I am 90% confident that the true population proportion is between 57.13% and 72.86%.
Say that again?
I'm 90% confident that the true population proportion is between 57.13% and 72.86%. Alright, good, let's just try another one. We wanna try another one, or we wanna just move on?
Try another one.
Try another, okay. I think, what was the next one? I
Try
suggested
another one, I'll move on.
18.
on the slides. Number 18?
Sorry, baby.
283, number 18.
Number 18, okay. So 283, number 18. Go ahead and start working on that one.
Number one.
Got it?
I can see it there, thank you.
Subtract the zero, oh, the top one. You subtract, 0.065 from 0.065.
And then the percentage of that is, 95%. So when you look at the chart of 95%, it is 97.8.
Sorry?
So it is 1.9.
283, number.
So that's 1.96 for the 95%.
Well, I do it in steps, yes, I do.
I could just like here,
Multiply it.
and I got this,
That's divided by, square root of that.
square root of this, so
So
then
usually, when that's on,
Mhm.
just hit the square root button right here.
Mhm.
There should be
I
one
should
zero.
get the square root.
Sure. Okay, so 90% confident, that means we're gonna get it right 90% of the time, you're gonna get it wrong 10% of the time. All right, and actually I'd like to draw the normal distribution, draw the bell curve. Yeah. Okay, so we're gonna get it wrong 10% of the time. So 5% of the time, we're gonna get it wrong by being too low, 5% of the time, we're gonna get it wrong by being too high. All right, so there's gonna be 5% of the data up here. So we need the z-value that separates the upper 5% from the bottom 95%.
Excuse me. Professor,
Yep.
Mr. Williams,
So, yep,
so
yep, exactly.
this
But the two tables. Yeah. Yeah, exactly.
Thank you.
That's pretty good.
So with this number, I put the whole number,
What do we get from the standard error? 0.009?
899. So I, 0095.
0.008995.
So this is your old, that's what I said. Cause this calculator got so much.
Okay.
That's
Can you
very
figure
good.
can you figure out how to store it? And you can just like.
No, it keep data.
What I would do is I would put that model, say how do you store it? But for now, just do that.
Professor,
Yes.
where did you get .81? Shouldn't it be .9?
95 is gonna be, for the z-score is gonna be 1.65. Here. So this is the closest one.
Good job, Dave.
This one goes 1.6. Wait, it looks like it's not quite lined up right, it's hard to see.
Oh, no,
So yeah, it's 1.65.
6996. It's .56. You know that one, right?
All right, are we ready to do this one? Ready? All right. So in this case, we're trying to find the proportion of technology resistors. Maybe we've got some product we're gonna sell people who don't like technology. Maybe we've got some training course. So we need to know the proportion of people who fit into that category. So we take a sample of 901 people, and we find that 9% of them are these so-called technology resistors. So our confidence interval is gonna be 9% plus or minus some amount. Well, that amount is gonna be our desired level of confidence, a z-value, times the standard error. So 95% confidence, what is our z-value?
1.96.
Alright, everyone good there? 1.96, so plus or minus 1.96 times the
I
standard
thought it
error.
was 1.65, wait. Yeah, I got it wrong. Yeah, I got it wrong, I'm sorry.
Yeah, so 95% means it's gonna be 2.5% in either tail. So you look in the center of that z table for 0.975. Alright, we have the formula for standard error. And what do we get when we crunch that? Actually,
0.08995.
0.08995.
895.
Okay,
95.
9.5. Alright, so
Another 9.
another
2
9.5?
9. Yeah.
Another 9.5. That's
No. Sir, 8995.
0.008995.
95. Yes. 95.
No,
How
I got 0.00909.
0.00.
Yeah, I got that.
I got 0.00895.
00.
0.00909.
Just take the
We
average.
got a lot of different.
No, cause you see, he said not to round it, cause I asked him, the 8995, he said not to round it.
Alright, go ahead, Elaine. What do you say more?
899.
8995. Alright, we'll go with Elaine's
I have the
unrounded.
number.
I got 402.
You got 4 zeros?
Yeah.
Yeah, I got
Did you forget to take the square root?
Oh, yeah. That's what it was.
Oh, yeah, with the square
Right.
root, with the square root, I still have 9535. Wait a minute.
Yeah, the
Zero, zero,
non-rounded numbers
I
should
have
be
0.09534.
0.009534.
Point 0095, what's that?
That's why I said you gotta round it.
0.975 and rounded.
Yeah, just missed the
4097.
number.
So it's 0.09553.
Okay,
Yeah.
unrounded?
I got it.
Put on your calculator.
95341. You got it.
Plugged in everything.
Yeah, that's right.
Oh, no, that might be right.
Now, how did, how did you get
Alright, so
I'll show you.
this is our standard error. So you're gonna store that in your calculator or keep it in Excel. 0.95. I'm gonna write it rounded just for simplification, but you won't. Alright, when we multiply the z-value times the standard error, what do we get for our margin of error?
0.0186.
You got the same thing.
868.
Okay, about 1.86% is gonna be our margin of error. So 9% plus or minus 1.86%. What do we get for the lower bound?
I didn't do that number. I
0.13.
did the other number.
Alright, and the upper bound?
0.0995.
I got
No.
0.10868.
0.10868?
Yes. I got it.
Yeah, so it should be 9 plus that would be something like that.
Yep.
Okay,
I mean, I think you were using 0.8.
Yeah.
81, that was,
Using 0.81.
that was previous.
oh,
So
yeah,
just, this has to.
sorry about that. That was,
Thank you, it was,
that wasn't my fault, right, dude?
No.
No, I'm sorry, it was my fault because I put 0.81 here instead of 0.91. Alright, so good exercise though. So can someone do the interpretation for this? It starts with I'm 95% confident.
I'm 90% confident that it's close to, between 0.078 and between between 0.1086.
Good, you got all the right pieces. Can someone else take it from the top? Christina?
I'm 95% confident that the true population portion is between 7.13% and 10.86%.
Perfect. Any questions on that?
So that's the number of the people that are technology resistant.
Yes.
And we're 95% sure, confident
Yeah.
that's about the number.
That is the number.
That's the number.
Yeah, if we were to sample everyone and they would tell us the truth, we're 95% confident that the real answer is between those two numbers. Take that to your investor meeting, get them to invest in your product that's gonna help those technology resistors.
Subtract it from 1, might have divided by 2.
Okay, good, good, so let's move on to proportion differences.
Right, but when you start out typically the most 700. So you have to do 1.16 times the square root. Right?
Right, so estimating differences between two population proportions. So technology resistors in Florida is 20%. Technology resistors in California, 9%. That's a difference of 11%. How confident are we that that 11% difference is accurate? Is it 15%? Is it 5%? Or is it something really close to zero, like there's no difference at all? Or is it the other way around, like actually people in California are more tech resistant than people in Florida? So we will answer those questions with something called the sampling distribution of the sample proportion difference. Like that? That has predictable sampling distribution properties. And we will use those predictable properties to build a confidence interval. What do we got going on here? Wow. Okay. So, need someone to read that title, tell me what that title means. Need someone to tell me this thing, why is it at the center of the distribution? I need someone to read this little formula to me. I'll handle this part over here. I'll start us off. All right, this is a frequency distribution, a graph of these things, of a whole bunch of these things. What are these things? Sample proportion 1 minus sample proportion 2. That's the difference between proportion 1 and proportion 2. So we did that 50,000 times, put it on a graph. This is what it looked like. This is the center of that graph. This is the standard deviation of that graph.
Since it is the right answer, the true
Yeah. The true what?
population proportion.
Proportion.
Common-
What's she
common
missing?
outcome.
What word is she missing?
Different.
Difference. Now we're looking for proportion difference. Okay, alright, so from the top, can someone read the title and tell me what it means? Alright, so reading the title is easy. And I'll give you a hint, what it means is, it's a frequency distribution of something.
Of the true sample though.
The frequency distribution of the differences between the sample proportions.
Yes, of the differences between sample proportions. How many did you calculate? How many of these differences did you put on that graph?
2.
All of them. All of them. Fantastic. So it's a frequency distribution of all of the sample proportion differences. So this sampling distribution of the sample proportion difference, well, what is that? That is